Hello, welcome back everyone. Another high grade chemistry lecture. I thought I'm gonna go over structures, okay, and bonding. Well, I did bonding yesterday. I'm gonna go over the structures that can form from them, okay. I mentioned a little bit about covalent bonding the other day, and you got the sulfur 8 and phosphorus 4, and these are covalent molecular elements, and you got covalent network and graphite and ionic, okay. I also mentioned in an earlier video about the different structures of molecules. Just a quick check over that. That's bent, okay. Maybe I'll make it a bit easy to see. Okay, that's bent like water molecule. That's what you call bent, okay. This is the pyramidal, like Egyptian pyramids I mentioned. So you got, that's meant to represent nitrogen and ammonia, and these are the three hydrogens coming off it, and it's a pyramidal shape. Okay. You got that's straight shapes, okay, like hydrogen chloride or something like that, or CO2, okay. Linear, okay, that's linear, like that should be a straight line, okay. And then you got the three-dimensional, goes in often all four directions. You got carbon in the middle, and these could be hydrogens to methane, okay. That's the fourth shape. Tetrahedral, that's tetrahedral, okay. So that's the fourth shape you get. So that's just a quick revision. Okay, so ionic, these are also called salts, okay. Sodium chloride, calcium chloride are examples, potassium chloride, sodium fluoride, magnesium fluoride. You get lots of positive and negative ions arranged alternately in the structure, forming a three-dimensional structure. So you get positive, negative ions, negative, positive, negative, positive, and they all fit closely together. So a combination of alkali metals combined with electronegative elements like chlorine and fluorine, okay. So this forms a three-dimensional structure, salt crystals. Table salt, I mentioned they're very stable, high melting points, okay. They so a lot of energy is needed to make them melt, break up. They do not conduct electricity as a solid, but if you melt them or dissolve them in water, they conduct, okay, because the ions cannot move much, okay. Okay, so that's ionic. So yeah, the ions can't move much. They do not conduct electricity as a solid, but they will do if they're melted or dissolved in water in solution. Okay, very stable, very high melting point because it takes a lot of energy to break them up. Okay. Covalent network. That is based on the tetrahedral structure, okay? But it's a little different. Instead you got every atom is a carbon. And diamond, as well as the carbide, silicon carbide and silicon dioxide, they also can exist as tetrahedral covalent networks, okay? So again, you got this tetrahedral structure all joined together. This is diamond. You got this tetrahedral structure. all joined together like this, forms a 3D, they form 3D crystals, networks. The atoms extend in billions of atoms in either direction, that way, up, okay, and form crystals. You know what a diamond looks like in a wedding ring. Obviously the crystals are a finite size, but at the atomic scale of atoms, they go on. There are billions of atoms in them. Okay. The covalent networks, they do not conduct electricity, so these will not conduct. Okay. They have very high melting points. Silicon dioxide is around about 1,610 degrees centigrade, but that's the melting point, compared to methane, which is, I mentioned that because that's a covalent molecule, covalent bonding, that melts at minus 182 degrees centigrade, which is why it's a gas at room temperature. These are not, the covalent network is not a small discrete molecule, meaning it's not a small thing, it's a very large network. There's no free electrons. That's why it doesn't conduct. Okay? The atoms are held together very strongly by covalent bonding, so it's very hard to break it, in diamond at least. And silicon dioxide, very hard to melt. Then you got, so I mentioned ionic bonding, ionic lattice, covalent network, and then you got a third type, graphite, pencil lead, okay, which is 6 membered rings, and they form sheets joined together. They form sheets together like this, where you get one layer, another layer, another layer, and another layer held together by weak interactions, okay, of the delocalized electrons. Each carbon gives 4 unpaired electrons, okay? Each of these is a carbon atom. Each of these vertexes is a carbon atom. You get 4 unpaired, I should say unpaired, not paid, unpaired electrons, okay? To make what we call delocalized electrons. So you get weak interactions between the sheets, and which holds them together. The significance of this is when you're using pencil, this isn't pencil lead, when you write with a pencil, these sheets get sort of scraped off, okay, flaked off, and that's what creates the lead in the paper, okay. They're very weak interactions between the layers, but the very strong bonding. The covalent bonds are strong within the actual layers, but the interactions are weak between them, okay? So strong bonding within the layer, weak interactions between the layers. And there's something called carbon 60. Forget these for the moment. Carbon 60, okay? Which is a spherical molecule called Buckminsterfullerene, discovered in 1985 by Harry Kroto. Buckminsterfullerene, a spherical molecule. It's a football shaped with lots of 5 and 6 membered rings. That means each ring is made of either 1, 2, 3, 4, I can't draw correctly, either 5 or 6 carbons, okay, 1, 2, 3, 4, 5, okay? They should all be the same length. So there's 5 or 6 membered rings, and there's also carbon 70, which is more elongated, and you get nanotubes as well, nanotubes. But the Buckminsterfullerene, carbon 60, looks a bit like this. This is my attempt at drawing a football-shaped molecule. So there's a 1, 2, 3, 4, 5 carbon ring, and then I'm attempting to draw 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. I'm attempting to draw a football shape, but you get the idea, I hope, that it's spherical, and these bonds are going away from us. Okay, this is a fullerene structure. Okay, hope that's a help. This is introduction. I will go into more details in other videos, but this is just showing you. So you got Buckminsterfullerene, you got covalent network, you got ionic lattices, and you've got graphite. Okay, there's the four: graphite, covalent network, ionic lattices, and Buckminsterfullerene. Okay. Yeah. I'll continue on next video.